Thank you. All right, it's working. Hello, everybody. Thank you for having me. Very fortuitous that I happen to be in Adelaide. My wife graduated next door today, or had her ceremony. I guess she graduated a few months ago, which was interesting. I didn't bother going to my graduation, so I had no idea how it all worked. I am going to talk about hot reload. Hot reload is something I work on. It's something that maybe you've used. I sort of work, so I work on the Roslyn part of hot reload, which is the very low-level engine that runs everything, which has been around doing edit and continue for years. So that's where I'm focusing my talks on. For disambiguation purposes, I'm going to talk about applying changes you make in code to a .NET assembly. That's the scope. The word hot reload means a bit more than that these days. It's a bit of a marketing term. With .NET 6, there was a big push for hot reload everywhere. And so there's XAML hot reload and there's web hot refresh and hot reload. I'm not going to talk about them. Some of them, because I don't know anything about them. Some of them I do, and I just, at some point you've got to stop talking. But if you want to ask anything specifically at the end about differences between hot reload and continue and F5 or Control F5, whatever, feel free. But I'm going to concentrate on .NET assembly, which means that I have to tell you what a .NET assembly is. So, what's a .NET assembly? This is a screenshot of ILSpy. Sorry, I don't actually really know where to look. I'm used to standing in front of my slides. This is very weird. Hopefully you can all read it. This is a screenshot of ILSpy. It is one of many applications that show you what's inside a .NET assembly. I happen to like this one because it's free and open source, pretty regularly updated as new things come out. And essentially there's two parts, there's two things in every .NET assembly. There is metadata, which is shown on the left, which is data about what's in the assembly. And specifically for this talk, there is metadata tables. There's a bunch of metadata that for all sorts of purposes, but for hot reload, we really care about the metadata tables in there. And then the other thing in your assembly is, of course, your code. But you probably all know there's not actual C# code in there. ILSpy is a disassembler as well, so that's what it shows you. But of course, you can turn that off. What's really in there is IL, intermediate language. And so they're basically the two bits, metadata and IL. And so for hot reload, to update a .NET assembly, they're the two things we have to update. So metadata tables is the main bit, really. It's the complexity. That's where the complexity comes in. So what's a metadata table? Well, the clue's in the name. It's a table, and you can think of it as a database table. In fact, you can think of your .NET assembly and the metadata in there as a relational database. There's even primary keys. Every row in every metadata table has a metadata token, which is essentially a primary key. If we look at the top table there is called the type def table. That's the types defined in your assembly. It's got a bunch of rows, bunch of columns. Mainly sort of when you first look at this, all you see is a bunch of numbers, and there's some letters there too, which shows you their hex numbers, and so you start to think, oh, these look like memory addresses or something, and that's when, in the past, my eyes sort of fog over and I move on to something else, because I don't really like this level of stuff. But trust me, there is some useful things in there. So relational databases have primary keys, metadata tokens. They also have foreign keys, and we have them as well. So over here we have the method list field. So the method, if we look at the second row of this type def table, it's the definition for the program type, which is where our main method is. So its metadata token is 02000002, and its method list field is set to 06000001. If we look in the method table, which is the next one down, we see a row with a token of 060001. So that method list field is actually a foreign key, and it points to the spot in the method table where the methods for this type definition, the program type, exist. So we start to see that it's a bit of a relational database. That that row 0601 is the main method. In this case, it's a top-level statements program, so I didn't write the main method, so it gets a funny name by the compiler, but it's just a main method. But so this looks like a relational database. All of these magic numbers, they're actually just IDs, and they're very clever IDs. And there's lots of little efficiencies and little optimizations done sort of in the name of these IDs, but also because of these IDs. So what are they? Well, it's a hex number, like I said. It's 4 bytes long, and any low-level programmer, which is the people who design this stuff, will see 4 bytes of information and think, how much can I cram in there? So of course it stores 2 different things, because why would you want something to make sense? But no, it's more efficient, right? We store more data in less space. So the first byte indicates which table this token comes from. This is where things get a bit weird as far as relational databases go, because this is not something you do, right? You don't need to indicate in the value of your primary key what table it came from, but we do in metadata, and I'll explain why in a bit. And then the last 3 bytes are the row number. And the row number is a very simple incrementing number. It goes up by 1. There's no gaps, never any missing numbers, can't skip any. There's no row 0, always starts at 1. But that sort of encodes a bunch of information in it. And the reason for that, the reason is efficiency, right? So the whole reason we cram 2 bits of information into 1 number is for efficiency. This is in every single DLL produced. So if we, when we compile your code, made these huge DLLs with these lots and lots of information in them, nicely laid out so that everyone could read them, you'd be annoyed because every .NET DLL would be, huge. So we wanted to get them as small as possible, so that's why we cram this information here. But we also kind of cheat. Well, not cheat, but we do weird things because of the power of encoding this information. So let me explain what I mean here. This method list, you can see it starts with 06, right? As I said, that tells you what table it's coming from. The method list example doesn't really matter, right? It doesn't make sense. The field is called method list. Obviously, it's going to come from method. But there is another field there called base type. I think my arrow points to, field list, sorry, field list. So field list points to 040000. I said there's no row 0. That means there aren't any fields in this type. But you can guess that the field table is table 04. This is all just numbers that come from the spec for the ECMA 335, 355, one of them. The spec for .NET, right? But so the base type one, this is where things get a bit more interesting. Notice the base type for the program class is 01, starts with 01. The base type for the module row above it starts with 02. Now it happens to be 02 and then all zeros, so it doesn't really exist. There's no base type for a module. A module is just part of every .NET assembly, don't worry about it. We could ignore it. But the point is, a type that you define has a base type, and that base type has to also therefore be defined somewhere. And it could be a type in table 2, which is typedef. So if you define a type and its base type is one that you've also defined, then its base type is going to be 02 something. But in this case, program doesn't have a base type, which means it inherits from object. Object is not in the typedef table because we didn't write object, so it comes from a different table, which is 01, which happens to be the typeref table, right? But so we've actually encoded, or using this encoding of 2 bits of information in our 1 token, we can provide a sort of an extra level of information without requiring an extra field. We now know this program class inherits from a type that is defined in some other assembly, just because the primary or the foreign key says so. And if we go and look up the 01 table, which is typeref, we find row D. So I really should wear my glasses sometimes. We find row D, it says object, great. I think there's more on the screen later. And so once you realize the first byte is the table it comes from, you see these everywhere, right? So I've highlighted on the screen, right? ILSpy neatly puts them in the actual header of the table. They're on the start of every token. All of these fields, if they start with, O, and well, not even O. If the first byte is a number, it's probably a table. Even to the extent, if we go back to look at our IL, If we look at line 12 there, which is the call to console write line, the fact that that says console write line is just ILSpy being nice to us. The actual IL doesn't say that. The IL specifies an ID. That ID is a token. And in this case, it comes from the table 0A. If you look on the left, you can see that 0A is the member ref table. Why method and member ref, I don't know, but anyway, that just means this is a member defined somewhere else. So even in the IL, we don't need to have separate IL instructions for call a method or call a property or, call a whatever. It's just call, but then the token tells us what to do because it encodes the table in there. So it's kind of clever. And if we go look up the member ref table, we find the row, right, which is row C. It says write line. It has a parent, which is 01. That's type reference. So that comes from a type that is referenced outside the assembly. We look that up. That comes from console. Great. That has a resolution scope field. I'm sure that name means something, but whatever. It's just where it's defined. And then we look that up. That comes from the assembly ref table. We look that up. And that says system.console. And so every single piece of information about that code calling console.writeLine is in these metadata tables, right? The code does not work without these, to the point of assembly name, essentially. And assembly name technically also includes assembly versions, but that's kind of an iffy subject depending on which .NET you're talking about. So this is also where the cross-platformness of .NET comes in. We have written console.writeLine, and all of the metadata says this comes from a method called writeLine in a class called console in an assembly called system.console. Wherever that assembly exists, however the runtime wants to find that assembly, that's up to the runtime. This DLL though, in theory, and in practice, but in theory, is fully portable to any platform, anywhere that runs .NET, because it doesn't have file names, it doesn't have doesn't have addresses into the DLL for where this method is. The runtime's job is to go and find a method called writeLine and a class called console in an assembly called system.console, however it wants to. So these metadata tables are really crucial. So the other trick with the other trick with metadata tokens though, they encode all this clever information, right? But we want efficiency. And we want to store as little as possible in your DLL. So all of the values in that token column there, the cool part is they don't actually have to exist. They're not in the metadata table. ILSpy puts them there because it's nice. But what is a metadata token, right? It's a table and it's a row number. And the row numbers always start at 1 and they always go up by 1 each time and they never skip and there's no gaps. And we know this because the database, this theoretical relational database, is written by the compiler into the DLL, and then it is never modified, it is never deleted, right? There's no updates to it. When you press build again, you get a whole new DLL. So the compiler writes out row 1, then row 2, and then row 3. The tables are written out in a specific order as per the spec. And essentially, the tokens can be fully computed when you read in the database. So let's say you have to write out the type table first. I don't actually know, but let's pretend that's the first one. The way you write a DLL is, well, you're writing one according to the spec, and it's going to be read by something according to the spec. So you don't tell anyone you're writing out the type def table. You just do, because it's the first one. And the first thing you have to do is write out the count. So you say, right, there are 3 rows. Then you start the first row, and you just start with the raw data. There's no need for IDs. When we read that in, we know we're reading the type def table. We've been told ahead of time, okay, there's 3, great, ready for that, start reading. But because we're reading row 1 and we know which table, then we know what this token would be. So we don't need to write it down. And so you get all these really cool things, like that method list field, which is called method list, but actually has 1 token, which points to the start of the method. It's the first method for that type in the table. That's because it doesn't need to point to the where it ends, because the next row in the type def table, wherever it starts, well, that's where the other one ends, right? And the method, according to the spec, the method table has to be sorted by the type that's in. So we get all these weird efficiencies by yes, it's a relational database, but it's also this highly specific format. So why did I bother telling you all of that? Because that's what makes hot reload hard. So how does hot reload work? Good question. That was only 15 minutes of distraction. This is how conceptually hot reload works. You write some code, you compile it, you send it off to a runtime, it executes it, you keep writing code, and away we go. This is not how hot reload works because this is essentially inefficient, right? If we compiled all of your code every time you did hot reload, you'd complain about build times, potentially change one character in a string, and all of your solution has to be built. That would be annoying. When we send it to the runtime team would say, what do you want me to do with all of this, right? You've just given me a whole new application. The whole point of hot reload and edit and continue is that it applies these changes, but it maintains the state of your application. And so that's where we get some complexity. So this is more like the process. And because I got better at PowerPoint between these two slides, we actually start in the top left this time instead of the bottom right. But so we write some code, we create a compilation. We call that compilation the baseline. And that's just the DLL, right? It's the thing you built. And we send that to the runtime, does its stuff, looks for its DLLs by assembly name, etc. Fine. But then we have these things called generations. And this is essentially every hot reload, every edit and continue, it's this little loop. And so a generation starts by you edit code. Editing code, you're doing in a high-level language, that's great. That's what we all like to do. If you edit a string literal, okay. If you edit something in a method, great. We have to then, we being Roslyn, have to then work out what has changed. So what edits have you made? But we have to work them out in terms of what makes up a .NET assembly, which means in terms of those metadata tables. So what do I mean by that? If you change the contents of a method, well, there was a method table, so you've changed that method. That, has a sort of an effect, meaning, well, you've also changed the type that that method's defined in, strictly speaking, and you've changed the IL for that method. So they're the three things. But it doesn't matter how many updates you make to that method. If it's all in the same method, you're essentially one update, right? So Roslyn has all these smarts to work out, take you from this high-level C# coding language you've written in into .NET. For example, if you change the contents of a lambda looks like it's in a method, but it actually is inside a method, which is inside a class, which is synthesized by the compiler. And so Roslyn has to know that so it can find the right row to update, right? It's not the method you think you're in, it's in another one. But anyway. So Roslyn does that magical work. The process for that is highly optimized to be as fast as possible because it happens while you're typing. It uses lots of algorithms that have long fancy names and links to PDFs where the algorithm is defined, and the PDF is from a mathematician, so all the variable names are one letter, and the code is kept that way so it matches the paper, but of course it means you can't read the code. So if you ever get a bug, you're like, oh no, is this a bug in? I don't want to. So anyway, longest common subsequence is the only one I know, but anyway. So then we get our list of here's what's changed in terms of .NET, not in terms of C#, right? And of course, hot reload and continue, it all works for VB as well, VB.NET, so that's important. So then we create a delta compilation. What that means is, we don't want to compile the full DLL. We don't want to compile the full solution. We want to compile as little as possible. So we create a compilation that contains just what has changed. And then we send that to the runtime, and we say, apply this delta. It's specifically a delta format the runtime understands and knows how to apply. And it does, and the cycle continues. That is one generation. So let's work through an example. Here I have a little class. I have 3 methods. Here I have some metadata table. It's got 3 tokens and a name. Great, ABC. They happen to be token 3, 4, and 5. Doesn't matter. That's just what they are. So I make an update to method B, or to a string literal in method B. Roslyn then works back from that and says, well, the smallest sort of unit of change here is you've changed the B method in the type called class. Sorry for calling the class. That's just a habit you get into when you work on compilery stuff. You're lucky it's not C. Most of mine are. So we make that into an update that says, okay, update class B. And so the compiler, or we then say to the compiler, hey, go and produce a delta compilation. And we essentially give it this list of edits is a to-do list for the compiler. It says, go and compile my project, but here's what's changed. Here's what you need to worry about. And so the compiler goes through and it says, okay, I got a class, aardvark. No, not on my to-do list, skip it. Next class, this one's called class. Okay, is that on my to-do list? Yes, there's something from there on my to-do list. Great. Here's my method A, is that on my to-do list? No. Here's my method B. That's on my to-do list. I will compile this method and I will output it. So that means the compiler produces a delta compilation with a method depth table that looks like this. It has compiled B. It wrote the metadata and it wrote the IL, and away we go. Now we modify A, and I took away the list of edits because it saves space on the slide, but also strictly speaking, we don't actually know them anymore in Roslyn. We lose that information. And we produce, I've changed A and B here. Sorry, it's subtle, that's why there's 2 lines. So we produce another to-do list for the compiler, this time class.A and class.B, both been updated. And the compiler, we give it the to-do list and it goes through and it compiles and it produces a delta compilation with method A and method B. So can anyone see the glaring issue that might arise here? Right? In this one slide, method B has metadata tokens for row 4, row 1, and row 2. How does this work? Well, so this is the complexity of hot reload, right? The only thing the compiler knows how to do is produce a DLL that is to the ECMA 335 spec. So that's what it does. And like I said before, these metadata tokens, they don't really exist anyway. So it's not like the compiler could even write a 3 for, method B in that second or first generation, because there's nowhere to write it. It doesn't exist. It's a job for the reader to compute these tokens. So we get this weird situation where we have to tell the runtime, here's a DLL, it's got 1 method in it. But actually what it does is updates this huge, whatever assembly that might have 1 billion methods. And we have to somehow tell it how it's supposed to update the right method when we've said, oh, it's method 1, no worries. So the way that works is there's some extra metadata tables that are for this purpose. And they exist in the PDB, which I haven't actually spoken about yet. So briefly, a PDB file, PDB meaning program database, so it just contains a bunch more data. That's it, a bunch more metadata tables. In the spirit of keeping your DLL small, essentially anything that is not required to run your code goes in the PDB. So PDB is to help you with debugging, to give you nice experiences. It's how things like you can go to definition and we can go and download the code from GitHub. That's using data in the PDB to pull that out. Not needed for runtime, so we put it in a separate file. That file's usually bigger than the DLL, and we don't care about the size too much. So you can see there's a document table, right? That's where we store file names. There's method debug information, there's scopes, there's all sorts of stuff. Custom debug information is my favorite one because that's where it seems to me like the people who wrote the spec went, let's just put one at the end just in case. And now every change I've seen to the PDB since I've been working myself always just goes in custom debug information. It's great. That is basically like a key value pair, and the key is a GUID, so we just add a new GUID into, like, here we go, this GUID means this now. Great. But you don't see anything there for hot reload. So you go look, that's the ILSpy, sorry. I forgot my slides. So you go look in ILSpy and you see this flag that says, oh, it's hiding empty tables from me. Whoops, okay, so let me untick that. And now I get a few more tables. I get state machine info. That one's cool. That one's where information about your async methods goes, so that you can step through your async methods and you can even update them. And we know how to make that work because they're state machines, but if you add a new await statement, you've just added, like, you might have 5 states. Now you have 3 states. And you were in state 4, but now you're on state 2. It's weird. But so we just bung all this information there. But still nothing about hot reload. And so you go and you download this ECMA 335 spec and you search for ENC log because David told you that's the name of the table. And you find exactly one result that says, oh yeah, there's this other table too, don't worry about it. And I just love it because it's just classic, you know, programmers are terrible at documenting their work. But so, you have to take my word for it. There are two tables in there called ENClog and ENCmap. There is one tool that will show you them, and it's called MDV. I put this up as a link just for completeness. I don't really expect anyone to use it. ILSpy does a great job these days. MDV was described to me as, in two sentences. Number one, it is the only tool you ever need to look at metadata. And that's true. But number two, it is designed for people who have read ECMA 335. And I have not. It's not actually that bad. But anyway, it's kind of funny. Okay, it's time for a proper demo. So excuse me while I look at my screen and get my glasses. Let's do this properly. So with Visual Studio, can you read that? It's not very exciting. So this is my ABC method. This is a little test app I have. So the actual tokens aren't going to be 3, 4, and 5. Let me just run it and pop it there and use Power Toys to keep it on top. So what this program does is it runs a tight loop, right, which is why you can see the time ticking over there, and it calls these three methods, and then it also outputs on the right-hand side the information from reflection about what methods are in this type. That will become useful later. But so this is just my proof that it's running. So we go in and we update method B, and we press the hot reload button, and it says hello from BV2, which is all cool. And we update method A and method B, and we press hot reload, and they both update. So, right, the system works. Great, there's my demo. Now we've got to get to the good stuff. So, a delta compilation never exists on disk. It is purely a stream of bytes. The compiler produces metadata, PDB, and IL deltas, and they're just a stream of bytes. They never exist on disk unless you're on this computer, in which case they exist on disk because I have a special flag set. So if I go into session 2, because I had to make sure it worked, so this is all of the stuff that edit and continue dumps for diagnostic purposes, because I have the diagnostics flag set, right? And so you can see here we have generation 1, we have the IL delta, this is the metadata delta, this is the PDB delta. We have generation 2, we have the baseline, which is the original DLL, and we have the code before and after, which you all saw me edit, so I won't need to bother about that. And what we can do is we can open up a command prompt. And so MDV understands and detects this format of files, this layout, and it knows what I want. So I'm just going to run it. It doesn't need any sort of help from me to run. So I will just run it, and then I will show you what it does. And all it does is output all of the metadata, much like ILSpy would. It just outputs more. So let me zoom. Have I forgotten how to zoom? There we go. Boo. That's probably too big. Is that all right? Cool. Okay. So it's going to dump out the original DLL as well. So this is generation 0 in its terms. This is not super interesting other than just to see how much stuff there is. Like, you know, there's just... I love like these things, for example, where the compiler, the C# compiler is creating attributes in your code for you all the time, but you never really know about it. So here's our program class. It's ID6, type 6, right? Helpers is just where all of my reflection output stuff goes. And then if we find methods, here we are. A, B, and C is 8, 9, and A. So that's where we happen to be in this program. And obviously this is purely dependent on the alphabetical? No, the alphabetical order of the files, I think, and then the order in the file of the classes. But you know, these can move around for all sorts of reasons. But so they happen to be 8, 9, and A. I'll just keep scrolling down. There's lots of metadata. There's every string. There's all sorts of things. Here's the IL. So now this is starting to dump the actual code. The methods should be visible-ish because they have strings in them which are easy to identify. Nope, not that one. There it is. So there's hello from A, there's hello from B. So these are my methods, and you can see up the top here, this says, you know, method 8, This is method 9, this is method A. Cool. So this is in the IL blob. There's a thing that says this is the IL for this token. Okay, and so here we go. So this is generation 1. Generation 1 is where we changed method B. So we have a much smaller output, obviously. The idea is to be as small as possible. But we have a method, right? We still have somewhere, no, we don't have a type def. Okay. So anyway, so our method B, here it is, and it's row 1, right? But as I said, this doesn't really exist. In fact, so ILSpy will show you the token for the row. MDV doesn't, because it doesn't exist, right? It does help you in other things, but so this is just row 1. It's not token 1, it's just row 1. But so what we have is these two tables, ENC log and ENC map. And these are the two that contain all of the magic for how hot reload works. And it's actually really simple when you get down to it, which is kind of funny, because like I could do this talk in 2 minutes without any of the background. It just would be very interesting. But so how do we tell the runtime that when we say method 1, we mean method 8, 9. And the way we do it is right there. There is a line in our log that is the compiler saying, I have emitted method def row 9. That's it. That's all it is. And so the runtime can use that information. Now, this doesn't map to, this doesn't say row 1 is row 9, but this is the first method def in the log table. So again, we can compute one of the keys by keeping track of how many method defs we see in the log table. And again, the log table, it has to be in this order, so all the method defs would be grouped together. So easy enough to tell. But so basically this is the first row that references a method def. Therefore, that's row 1 from a method def table in this generation, and it says 9, and that's it. If we go back to our relational database sort of analogy, this is update the method table, here's all the fields, all we need is our where clause, where the token is, oh, it's a 9, we get it from here. The ENC map says essentially the same information. In this example, the ENC map is not useful, or doesn't add any more information, but there's other types of edits you do where the ENC map becomes more useful. For example, if you add a method, then you have to update the type as well, and so the ENC map tells you which type you're updating when you add the method. And like there's an edit that kind on the end which says add or update, you know, that's another flag. So for this example of updating one method, the log or the map, either one would work. You know, it doesn't need both, but that's what the compiler outputs. And by the same token as above, right, the first method def output, so therefore we know it's row 1. If we scroll down, we see the IL. Now the IL, because it's in a separate blob of data, it actually already just says this is the IL for row 9. It doesn't have to do any mapping, and it doesn't, you know, it doesn't conform to the same thing. It's not a relational table, whatever. It just says here's some IL for row 9, for method 9. And generation 2, you know, same thing. We're going to see method A and B, 1 and 2. We're going to see 2 entries in the ENC log. Again, the first one is 8, therefore it's A. The second one is 9, therefore it's B. Map is also useless, and there's our 2 methods already with the right things. And so the runtime takes this information and it performs the update. Now, what does that update involve? Well, the way I like to think about it, because it makes sense in my head, if you think about reflection, what you're kind of doing is you're kind of querying this relational database, but it's the in-memory runtime version, right? The runtime's going to read your DLL. It's going to grab all the data out of the DLL and put it in memory into its reflection database. And so what you're doing here is you're saying, just update all the fields. So find row 8 and every single field you had, just clobber them with whatever's in this new row that I'm giving you. Find row 9, same thing. For the IL, same thing. Here's the IL for the new method. In these days, well, not just in these days of tiered compilation, but even in the old days with jitting and things, you know, it has to reset a flag that says, yes, this method needs to be jittered again because we've changed it, so it does all of that. But essentially, that's how it works. The IDs get, the tokens of the methods get to stay the same. So any call that used to call token 8 still calls token 8. We've just updated the code. If we did anything that affected any of the metadata, any of the data in that row for that method, then that would also have been updated. And the world continues. That's how Hot Reload works in a nutshell. Told you it was a short talk. So any questions before I go into some more stuff and have more fun demos on any of the metadata-y anythings? David.
There's a question from Ian. Do I always have to save changes before hot reload?
No, you don't. One of the cool things, well, not if you're using Visual Studio. One of the cool things about Roslyn is that it's always got an in-memory representation of your code, and so it is more than happy to identify the changes you've made without you hitting the disk. It doesn't use the disk, so no. In fact, yeah, you can use that for some fun as well. Well, makes some things easier. I'll show you later. Any other questions? Yes.
I find it intriguing and sensible as well that your code is matching the papers that it's based on. Is there like any contention about trying to get the mathematicians to use more than one letter for the variable to make them come and help debug?
No, I don't know. These are, well, everything that I've seen has existed before me, but no, I think they're pretty well written papers if you understand them. That wouldn't be a bad idea as someone who's had to debug them and like, well, what was K and N and V again? But that's what mathematicians like to do. Fortunately, those bits don't go wrong, let's say, touch wood. They're not the bits where there's problems or bugs usually, unless it's our interpretation of that paper, in which case the variable names being the same actually helps. So, yeah. So that was a simple scenario, which doesn't really illustrate all of the various complexities. So in order to illustrate the complexities, but also possibly answer some frequently asked questions, which is, if you've ever come across something and it says, well, I can't remember if it actually says root edit in the error code anymore, but they're known as root edits internally, and I think we talk about them as root edits anyway. If you ever come across an error that says ENC, blah, 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 and it'll be like cannot, sorry, I'm just going to check that wasn't my battery. Nope, good. Making a ding. It says, cannot apply an update to whatever. So they're called root edits. And they are things that hot reload cannot do, or edit and continue cannot do. So why not? There's a few reasons and some example scenarios to highlight them. So updating records. So records was a new feature in C#9, and when they first came out, if you tried to change a record, it would say, cannot update a record. The reason for that is, in general, every new C# feature by default won't be supported because we have to teach Roslyn how to support it. And by that, what I mean mainly is, well, the main thing we have to teach it is the to-do list for the compiler, right? The contents of this Delta assembly are .NET-isms, not C#-isms. A record is purely a C# thing. It requires no runtime changes, right? So it's just a class under the hood. And it comes pre-generated with some code that does some stuff that makes them work, but it's just a C# concept. So when you change a record, let's say you add a field to a record. Well, what hot reload needs to tell the runtime, well, and the compiler to compile, is a new field, but also an update to the toString method, the clone method, the copy constructor, the print members method, the equals method, and the getHashCode method. They're not difficult things, right? Those methods aren't special. The compiler knows how to compile them and it will emit them if they're on the to-do list, but something has to tell Roslyn that this matches this, right? So sometimes with new language features, it's just a matter of going in and doing that work. And then sometimes it's more complicated than that because, for example, if you have a record and you define a member called print members, well, the compiler won't emit one. So what to your C# code looks like adding a method is actually going to end up being updating one because there was one, you just couldn't see it. Now there's one you can see, but we have to know about that. And then same thing if you delete it again, well, you didn't delete it, it's still going to be there, but the compiler's going to. So there's complexity there, and sometimes there's still root edits that can happen even after we've taught a thing. Sometimes the work we have to do is actually like, it's kind of like negative work. We just comment out some code. So for example, updating namespaces used to be a root edit, and because of some other work we did to restructure how things worked, we actually can support namespaces now, and the PR to support namespaces in NET, it literally commented out a line in a switch block that where if it saw a namespace declaration, it would issue a root edit, and now we don't want it to, and that's it. We didn't actually have to do any other work because everything else worked. But so there's always something. The edit and continue hot reload code is highly tied to the language and to each language, right? C# and VB. So sometimes it's that. Why couldn't you update attributes? You didn't used to be able to change attributes on methods or classes or anything. That would stop hot reload. Now it works. The reason for this one we thought was going to have to be a conversation with the runtime about how they could do some work to allow us to update the attributes. So attributes are stored in their own metadata table, and the runtime just hadn't really had any code that would handle updates. But it turned out in talking to the runtime team, they actually didn't need to do any work, and it totally would work. We just had to teach the compiler to always write out all of the attributes for a method, not just the ones that have changed. And so that one's a matter of kind of sort of cheating with the metadata. An attribute, a row of an attribute points to where it belongs. So it points to the method or the type or whatever, and it uses this cool thing of the fact that the metadata token tells you which table it's for, right? And so the types, the methods, the fields, all that, they don't know about the attributes. The attribute table kind of stands on its own 2 feet. It's pure data that links off to things, nothing links to it. And so we were able to sort of abuse that notion by, if you change an attribute on a method, or if you add an attribute to a method's a better example, the attribute table has to be in order according to the spec, and the runtime hasn't done any special work to allow any magical weirdness of ENC logs and maps and whatever. So all we did was we taught the compiler, if there's any attributes, just emit all of them. And so it just rewrites the entire attribute table every time, which means if you add a new one in here, we don't have to do any magic inserting, it's just going to appear in the right order. The one in row 4 used to be for property X, now it's for field Y, but he doesn't care because it's just a row of pure data. So sometimes it's like, not really cheating, but abusing the metadata format. Why couldn't you add await and yield return? I kind of mentioned this one before with that state machine table. That state machine table that keeps track of what you do in asyncs and yields, iterator methods, it just didn't have enough information that we could reconstruct the state machine. And so we did some work, well, not me, but someone did some work, and now they work. So sometimes it's just a matter of, storing more stuff, which we're generally happy to do. It's in the PDB, and it's only written in debug. This is a tooling concern, not, if you do a command line build in release mode, you're not going to worry. Blazor WASM is an interesting example. So I said that metadata helps .NET be cross-platform, right? It's up to the runtime to work out where system.console is. So Blazor WASM's case, if you say I need this assembly named system.console, it's got to go and download it from your server, right? But we don't have to worry about that. But what is different is not all runtimes are equal. And Blazor WASM runs on mono. And the mono runtime never got any work, from its inception, it never got any edit and continue support other than changing a method. And so that was all you can do if you're targeting Blazor WASM. And there's a handshake that the runtime does to Roslyn that tells it what it can support, and so Roslyn knows to issue root edits. But so you might have something that works in this project and it doesn't work in this project, and that's because the runtime doesn't support it. So now the mono is getting a lot better all the time. It supports a lot more now, but there's still some edges there, and you still might run into that. Sometimes, the runtime has a bunch of code, and it's all written in C, sadly, which means I don't want to read it. But it has to, take these delta compilations and do work. And so the mono team just left off some of that because they had lots of work to do. Totally fine. And then generic types. Generic types is one of the bigger limitations to do with there's just so much work in the runtime to support this that is going to take a concerted effort from everybody involved in order to make it happen, which is not to say it won't happen, it just needs a concerted effort. A lot of the root edit things, on Roslyn, I can go and, I think I've actually got it bookmarked, where I can find the list of, in the last 7 days, how many times each root edit happened on every Visual Studio developer's machines, right? No names associated, I promise, just a count. But so we can tell what is the most popular root edit. And we can then use that and go, right, well, let's fix this one, or maybe come up with some way to fix half of these scenarios, right? Generic types is one where we're just going to have to, it just needs a bunch of teams from Microsoft to all come together to work out how can we make this work, because the type system is just so heavily involved with generic types. So, my favorite demo, and speaking of top root edits, committing crimes. So one of the top root edits for hot reload, editing continue, was, or is, sort of the top, well, within the top 10, there's a couple of scenarios that we sat down and we designed how we wanted how we could possibly fix these, and we came down to one base level thing, which was deleting a method would enable all this. So things like changing the return type, changing a parameter, or adding a parameter, removing a parameter, renaming a method. All of these things were top root edits, and we worked out that if we can add deleting methods, we can make all these work. So let me show you what that looks like. So I've just run my app again, right? Nothing magic. I'm going to delete this method, and I'm going to press hot reload. So you can see the time is still ticking because this program is running a loop, and it's got a try catch. You can see there where it says calling C, it says a problem happened. This is, does the door not open from the outside? So this is because method C threw an exception. And in this case, it threw a missing method exception because I deleted it, which makes sense, right? So this was a root edit. Now, this kind of seems a little bit useless because it is unlikely that in your code, around every method call, you'll have a try catch missing method exception just in case someone deletes it. But it turns out that, well, it turns out two things. Number one, if your app can continue running, you're better off, right? So for example, someone asked about saving a file. Well, I didn't save the file. I can Control-Z, method C is back, and my program still runs, right? So as long as you've got some exception handling somewhere, you'll be right. And this is kind of the goal of hot reload, right? The idea is you get to keep working without having to restart whatever it is, right? Your app, your website, you don't have to navigate through a bunch of screens to get to where you were testing, whatever. And all of your state should be there as well, so you don't have to re-enter any forms data, all the things. So the idea is just to allow you to keep going. So that's why we allow it. But the other thing it lets me do is I can, for example, let me make this return a string, and I will hot reload. So what happened here? There's a couple of things. So number one, method C threw an exception again. And you'll have to believe me that it's a missing method exception, but it is. But C still exists. Well, the reason is, of course, in C# and in .NET, well, definitely in C#, you can't overload a method by return type. And, well, no, actually that's not true. Even if you do overload a method, you've still got two methods, right? The method C that was being called has no return type. I haven't changed the return type of a method because you can't do that. But what we worked out was, well, if we just delete the old one and add a new one, that's totally fine. And .NET is totally fine. The metadata table doesn't care if it's got two entries in it with the name C, as long as all the IDs line up. And so on the right-hand side now you can see there's a new method at the top. Now it's added at the top. I don't actually know why. I'm assuming that's a weird quirk of reflection because this was, it was a row 1 in a Delta update or something. I'm not sure why, but anyway. At the top we have a method C with a return type string, but at the bottom we have a method C with a return type void. So we have two method Cs now. One of them you can't see and it throws a missing method exception. But in the runtime, there's still both. And in fact, that's because the runtime doesn't support deleting methods. In Roslyn, we just lied to the runtime. when you delete the method, or when, in this case, I change the return type, it literally updates method C and it makes the method body throw new missing method exception. That's all it does. It's really great. Now, the reason that the call to C failed though is because if we go up here, this code compiles. This is fine. If I hover over it, it says this is a method C that returns a string, right? But here's the quirk. This is my main method. I didn't change this. So the compiler didn't emit a new copy. And so there's a copy of main, which points to method C, token A. It's still running, but method C that's token A now throws. There's a new method C, token presumably B, that doesn't throw. And we're smart about it, so I can put this back and hot reload. And we resurrect this old method C because we find one that matches, and we're like, oh, here you go, make it a zombie. So we're trying not to fill up your DLL with just a billion methods, but we'll get there. But so what this means is that it turns out deleting a method, and that's a pretend deleting a method, is key to all of these things. So you can rename a method, we just delete the old one, add a new one. We still don't support renames, but we support adds and deletes, right? Adding a parameter, same thing. We delete the old one, we add a new one, new parameter. Where this gets fun, let's see if I can do this. If I add a new property, and I hot reload, so on the right, we now have two new methods. So a property in C# is two methods in a trench coat. It's a get method and a set method. An event is also two methods, an add and a remove. In VB.NET, an event is three methods because there's a raise event too. I just like that fact. But so now we have two methods there. If I change this to an int and hot reload, oh no. Oh, I've got a bug in my reflection printing code. See, this is what happens if hot reload doesn't work. My app crashed. Now I've got to start again. But so you can just see, right, we have this explosion of methods now, because now we still have our string getProp and setProp. Now we have our int setProp and getProp as well. So if we didn't resurrect these things, it would just explode. Now I have to restart this again. Anyway, I just love the fact that you can do this. And it's kind of a hack, but it's kind of a pro tip. Let's see, so I can't make this async void, right? This is a root edit. Oh, no, it's not. Well, if I press hot reload, it should be. Oh, maybe I can because it's void. Anyway, oh, there we go. Now it's happy. Oh, sorry, that's right. You can make it async, you can't make it non-async. So this is a root edit, right? Because I just modified this method. So, little tip for you, if you delete the method, that's totally fine. You can delete an async method, and then you can hot reload. And then you can create a method that's not async. Well, that's fine too. We support that. You trick Roslyn. Now, that one, the reason that's a trick is because, of course, you would have lost any state that was in that async method. Right? This is a root edit because Roslyn is trying to do this without losing state, and it can't. And so you're manually sort of saying, yes, that's fine. But it's a nice trick. The other cool thing, the other quirk of this, and I think I'm just going to start again because I have no idea if I've confused it enough now. So the other thing that just to be aware of, I guess, if I delete method C again, we have a compile error now in my main method because method C doesn't exist, right? But I hot reloaded and everything was fine. This is again based on it does a delta compilation. Nobody touched the main method, so the compiler, when I pressed the hot reload button, the compiler never looked in the main method, so it didn't see that it couldn't compile it, and it didn't compile it, so no problem. Right? That's why we now have this sort of orphan method here. This is why I say it's committing crimes, because this code doesn't compile, but it's happily running, and I just love that. The other thing though, so you can get yourself in this situation, and if it seems weird, then that's fine. Just make a change, right? And then hot reload, and everything will be, well, it might not work, but it'll be what it should be. Whether it compiles or not is up to you, but the state will match your mental model. So sometimes you need to modify some methods just to get the compiler convinced that, hey, something's happened. But the other thing with hot reload makes sure that what is in memory in the runtime matches your code. What it cannot do is it cannot run your code for you. So even if let's say I'm going to comment out all of these lines, and I'm going to press hot reload. And you'll notice that my program didn't change. It still says it's calling C, even though I commented out those lines. Now the reason for that, the main method has been updated. You have to take my word for it, but I promise you it has. Well, I mean, I can show you the MDB output, but it has. But what hasn't happened is that nothing is running that new main method because the old one is there running in a tight loop. Now this is the difference between hot reload and edit and continue. Edit and continue, it would have updated the actual running instance of the method. Hot reload doesn't. It's a little simpler, slightly less scenarios, but easy to use, you know. But so, because it's in that tight loop, it'll never change. The runtime will never see the new contents of the main method. So that's the other thing to maybe be aware of. This comes up particularly in, well, I mean, the best example these days is anything in your startup CS, program CS usually, like ILSpy.NET, right? Where you're binding up all your collections. If you've got automapper configuration or whatever, you can change that class and you can change that automapper configuration for that class, but nothing's going to run your startup CS again, so it won't take effect. The ILSpy.NET team are trying to enable all of that, and hopefully they'll get there somehow. But for now, you have to be aware that your code needs to actually run, and sometimes you need to do it. Which brings me on to my last point. If you really want to get into making this stuff work, there's actually an attribute you can apply. So let me open a project here and hope that my Git repository is in the right state. Be code, oops. So this is code to a game I wrote. And being a game, I want it to be fast and I want it to work at 60 frames a second. So there's lots of caching in it. And there's apparently a class called that. Great. Hang on, so yeah, so there's lots of caching in this app to make it go fast. But of course, when I apply hot reload, so it's a train game, you draw out tracks, you put trains on. I don't think I have the code in this branch, sadly. But anyway, when you draw out the tracks, it caches what they look like in a bitmap because, in theory, they don't change much. The problem being, if I then tweak the hot reload code to say, oh, actually, I want this to be drawn with 5 pixels instead of 4, I want to see what that looks like, but it never changes because that bitmap doesn't get redrawn. So there's a special attribute you can add to your code that your code will get called when any hot reload happens. No, I don't have it. Maybe in here. Bear with me for 2 seconds. Oh God. So there's an attribute you can, no, okay, I give up. There's an attribute you can add to your code, to a class, that your class will get called. So you create let's just randomly do it here, a static class update handler, and you put up here and you go metadata update handler. And so what this will do, have they added an analyzer? Oh, I need a, oh. Yeah. So what this does is, and now I'm not going to do it because I can't remember the syntax, but you create a method in there called, like, I think it's called after apply or something, and it takes in an array of types, and the runtime will call that method with the types that have been updated. And so you can do whatever you need to do. So, I mean, being lazy, you just clear your cache and let it rebuild on the next one. But if you want to, you go inspect those types. You go, oh, this has changed, do this, whatever. That's if you want to get really hardcore in allowing hot reload. It's very advanced. But if you Google for metadata update handler, it is documented, that one. And so that's it. That is the last question slide for this, even though I had two. Does anyone have any questions about anything at all? Hello.
Another question from Paul. So what project types are supported by hot reload?
So this is a very good question that I'm not a great authority on. So being on the Roslyn side of things, this works for C# and VB. And as far as I'm concerned, this works for every project. But again, whether the runtime that you're using happily applies those updates and can run that code again is maybe not as easy an answer. But yeah, so C# and VB is the general answer. This is edit and continue hot reload is a Roslyn feature. So F# doesn't use Roslyn, it's not supported. They could add it if they want. I suspect with F#, the way that you do F# development with F# interactive, it's probably not as necessary, right? Functions stand on their own 2 feet and you just call them and see what happens and, you know. But yeah, so from the Roslyn point of view, C# and VB, the runtimes is where things start to get a bit more grey. You know, as I said, Blazor uses mono. There's probably there's differences sometimes between operating systems because of different quirks in, you know, Mac and Linux. Phones and things and MAUI versus WinUI, etc. I do not profess to know the answers. It's usually a matter of try it, and if it doesn't work, Google and see if it's just you or if it's an actual bug. But there's so many variables that have to work for the update to apply, but for the code to run again is the thing. You know, like, yeah, the WinForms team had to go do some work to make all of the forms repaint when there's a hot reload of any form data. And so MAUI and Xamarin, they all have to do all of these things to make these things work. So sorry, I don't have a good answer for that.
There's only support for .NET Core 6 upwards.
No, there is support in, so the runtime, as I said, the runtime can communicate to Roslyn what changes are supported. So there is support for a feature set in any .NET framework because edit and continue essentially formed the baseline, and edit and continue is supported in .NET framework as well. But .NET 6 was a big push for new features. So things like changing attributes, some of the stuff around lambdas, renaming methods, that sort of thing, those newer features are more likely to be limited to .NET, to .NET 6, 7, etc. But there's some stuff that will work everywhere because it is built on edit and continue. You had a question?
Yeah, are there any gotchas with lambda expressions?
There are lots of gotchas with lambda expressions. Lambda expressions are hard. Lambda expressions compile, if you haven't ever seen it, well, where am I? Is there a time limit on these things? I'm just gonna talk.
Pieces late anyway.
There you go. I want to show you SharpLab because SharpLab is fantastic. I've got to write a lambda expression that returns a 4. And I don't want to see IL ever in my life. So a lambda expression in C# compiles to this, which is a helper class with an unspeakable name. Unspeakable meaning the C# compiler makes it's valid in .NET, but it's not valid in C#, which means it can go in the assembly, but you can't ever write it, which means the compiler never needs to worry that it's going to step on your toes and emit a class that you've written. But so it gets a class and a helper method and a field, and it initializes the field here and it caches this field for later. And sometimes it doesn't because it can't, and there's all sorts of smarts around it. And so, yeah, this is, lambdas are hard because, so, you know, this is an update to method M, but really what it did was change that helper class method whatever. So we need to find that out. And if let's go and do this, and we go plus A, yeah. So if I added that as part of a hot reload, that helper class now got a new field, which means we need to issue another type of update to add a field, but not all runtimes support adding new fields. And so we need to know that. So some Lambda updates are okay. There's also things. And then the big problem there is at the moment, we're not that smart. So when I say we need to detect that, we actually don't because we're not that smart. We cannot efficiently enough tell whether you've captured new variables in your Lambda change. And so we just don't let you change any captures. So if you captured 4 variables before and you do a hot reload, as long as you still capture those same 4, we're fine. If you add one or remove one, sorry. Even if that one wouldn't have caused, like we just, yeah. There's some level of complexity with Lambdas especially, where we just sort of go, nah, this is too hard. It would take us too long to verify this, that you may as well just recompile your code. So there's lots of edge cases there, but Yeah, they are. We try to treat them as just normal methods. They're just not where you think they are. I don't know if that answered your question at all, but I talked for a bit. So, any other questions?
If you have a legacy Windows Phone application that doesn't work with hot reload, what can you identify what's the problem? How can you identify why it's not working?
That is a very a difficult question. So it probably is it's probably that, ensuring your code runs again. I know the WinForms team added, so that attribute I showed you, like they have code that does that.
You create
but
Windows Phone application, how do you work?
Yes.
But you want the one that it's built to the same target.
The same target framework?
And then the one that dummy one doesn't work, and the one that you got doesn't work.
That is more difficult. Unfortunately, I don't think there's any good answer to that other than looking at the code of the real one and seeing what the differences are. And
the build system is quite complex.
Yeah.
That we got to analyze the generated code behind working this kind of stuff.
Yes. So I was going to say one of the big problems with complicated apps can be how, not that it's a problem with the build system, but so between Roslyn and Visual Studio or .NET Watch and the debugger, they have to know, where is this DLL? Where does this code fit into this overall thing? And there's a lot of scenarios specifically around like plugin loading. If you do any kind of dynamic loading of assemblies, it's very hard for all those components to understand that this code is actually the code that's running over here. Under the debugger has a lot more smart, so edit and continue might work where hot reload doesn't sometimes. But yeah, unfortunately, it's really hard with complex apps, and because it's usually it's a different answer every time. And unfortunately, the only thing you can really do is, so you take your new empty project and that works, and you sort of slowly introduce a bit of complexity and go, oh, well, maybe it's this thing. And you introduce a version of that here and see if it still works. You essentially, yeah, exactly. You essentially just bisect. That's all we can do. There's plenty of bugs where we have to investigate the same thing. There's common things. WinForms should be okay. Things like WPF apps, because they use generated code. One thing I've run into a lot is if you use an asterisk in your assembly versions, then generated code can often break it because you're not allowed to change assembly version for a hot reload. And so any generated code, even if you don't change the code, your generator is probably running anyway. And so then the runtime sometimes sees that as a version update. So you just remove the asterisk from the version number and then that'll work. But there's just 1,000 different scenarios. Yeah, especially when it comes to generated code. And generated code isn't special, right? Hot reload sees all of the code changes as though you wrote them. So if you didn't do a root edit, but your generator did, then it's still a... Yeah, it's still seen by the compiler because it has to be compiled, but so it still can't do any of the root edits that you can either. So you have to be very aware of what your generator is doing to know, you could be getting a root edit from generated code that because you can't see the generated code, there's no squiggle to see, but that could be what's going on under the hood. There's, unfortunately no one answer to that one. Any other, yeah?
What kind of wacky things can you get if you mix and match hot reload with edit and continue?
It's actually not, you can't, essentially. So the debugger is involved in both. It's just whether, so there's a thing called an active statement, which is which line of code is actually running. And the debugger and Roslyn sort of track that in unison. The debugger tracks it and Roslyn maps it to a spot in the code. With edit and continue, that is essentially turned on. And there's a few things like if you can't delete an active statement, you can't rename a method if the active statement is in the method. There's a few things like that. We can't do things around next to it. But apart from that. The rest of it's all the same. The difference is the debugger and Roslyn work together a lot more to save. So they save more of your state because that method is updated as you're stepping, and so all your local variables are still saved, etc. Hot reload is the simpler scenario; it doesn't have to worry about that. But it also just means that, like, if you have a debugger attached, essentially hot reload's turned off, editing continues turned on. If you detach from the debugger or you're not paused on a breakpoint, hot reload is turned on and editing continues turned off. They're mutually exclusive. Yes.
Can the hot reload be improved in the future as well? For example, if you want to reload the application, you need to always click on that fire button. Can it be improved in the future? Like, for example, same as React. Like, if we just need to save the file and the application automatically reloads.
Yeah. So that's.
Expect that in the future as well.
You should be able to expect that right now. I believe that works. Let me go back to my app so I can run it, because I have no idea what this is doing. But there should be, if you click this little button, yeah. So go Windows. There it is. So yeah, so there is hot reload on file save. It is there. That should work. As far as improvements in the future, it is always getting improved as well. Every new C# feature, in theory, works with hot reload and editing continue. In practice, sometimes that's because the compiler dev makes it a root edit and says that's good enough. But you know, then we'll usually come in after the fact and try and clean up. But that also depends on the feature, because you know. So David mentioned that there's a few new C# features to come out. So one of them is using aliases got improved. Well, I can tell you, I can pretty much guarantee that there's no effort needed for hot reload for that, because that is all just how the compiler finds types. And it's purely C#. What it writes to the DLL once it's found those types is not going to change, and so hot reload should work. Primary constructors, though, is the other one, and that definitely doesn't work with hot reload. And that one is a very big question mark. Like, literally have been in meetings as to whether it will ever work, because it's very complicated. And there's things that if you have a parameter in a primary constructor and you don't use it, then anything that was passed in for that value, for that property, does not exist anywhere. It's completely lost. The compiler never touches it, never sees it. And so, but if you start using it, that's what you're going to expect it to have its value as, and we can't make it up out of thin air. So, you know, it is always getting improvements, but at the same time, it's also, you know, death by 1,000 paper cuts kind of thing. Yeah.
How many issues have you found basically hot reload and the Visual Studio debugger stepping on each other's toes?
Well, I mean, hot reload like the debugger team is a very big part of hot reload. So none really, because the debugger is how hot reload works. Even hot reload, when you don't have a debugger attached, the debugger is involved, and the debugger actually orchestrates the whole thing. So yeah, that's not really. It's not really stepping on its toes. Like, that is the debugger's job, is to be there involved. And I mean, there's been bugs, obviously, but yeah, it's not like we're not competing. We work with them. I have a monthly meeting with the debugger team. Yeah.
In that case, how have you done much seeing how hot reload interacts with Razor pages?
Funnily enough, my main job is actually on the Razor editor in VS. So I'm well aware of Razor. The Razor case is very interesting. Slightly off topic, but I'll answer it anyway because we're waiting for pizza. So Razor works with a source generator, and unfortunately, Razor generates two different files for two different C# files for every Razor file. There is one file that the editor uses to make the editing experience work, and there's one file that the runtime uses to make your web pages work, right? So for the editing experience, for example, none of your HTML is in the generated file at all, because it doesn't matter. For runtime, obviously, it's highly important, right? So there's huge differences in these two files. When you hot reload, if you're running your app and you're looking at a Razor file, you're sort of looking at the generated file for the editor. And then you make a change and press hot reload. What you're saying is spin up all of the runtime code generation, then work out where that change was there, and then apply it. And all of that makes it very slow and very complicated. So the solution is being worked on, but it is a very long, drawn-out process. There's a bunch of things that have happened. Cool. So the Razor compiler is now owned by team members who are on the C# compiler team, and the Razor tooling is now owned by people who are on the Roslyn IDE team. So we're all in one team now, and we're all working together, but it's very complicated. So we have to get these two files into one without breaking anything, which is hard. We have to get the source generator used via inside the editor as well, because right now the editor doesn't use the source generator, but runtime does, and so there's another split there. So we have to unify all this stuff. And then once we're unified and everyone's talking about the same thing, then we can actually reason about what's going on and go from there. Is the long-winded answer that I should probably write down, because that's what I have to say for my performance reviews. That's what I'm working on. Any other questions? Are we all excited for pizza?
What would happen if you had an application that you were multi-targeting sort of two different runtimes? Is it a different experience depending on which ones?
Yes, it is. It gets very weird. So the debugger manages all of that. So in Visual Studio, you can have multiple startup applications as well. So you can, when you press run, it could run 7 different processes, and the debugger manages all of that, and it keeps track of all 7. And when you update this file in this project, between it and Roslyn, we know that these 3 processes need to be updated, but not this 4th one, or this 4th one sometimes. And the debugger knows that this process is on this runtime, and these are the capabilities. And so when Roslyn compiles that, we get those root edits. But when it compiles this one for different capabilities, we get different root edits. And yes, it can be that you make one code change, and it can apply to half of the things you're running, but not the other half. So things can get weird. But yeah, the debugger manages it all, and we try to do the best job we can and get as much of your internally, and I think externally, we call it the inner loop, where the inner loop of development is you're sitting at your editor, how long after you've typed your code until you can actually see it running. And we want that to be as fast as possible, and so we also want as much of that to work as possible. So if we can only update 2/3 of the applications you're running, fine, that's better than none. So we try not to say, no, I can't do everything, so I'm not going to do anything. But yeah, it can get weird, because you could end up that your .NET 8 app running here and your .NET Framework app, which is the exact same app, one of them gets the new button and the other one doesn't. It's possible. I think that might be it. Cool. Well, thank you for listening.
Question not related. Is monoSysL considered as a legacy project?
I don't know. That's a very interesting question. I don't know. I mean,
Because we have a debate in the team that
yeah.
we should not use that anymore because it's old and legacy, and the other one say, oh, it still get updated, it still get maintained.
I would. I mean, I don't know the answer specifically for monoSysL. I mean, mono is worked on and improved, and again, the end goal, I think, is unification with .NET. So there's only one runtime, but while there's not, then it's sharing as much code as possible. So there's active effort in mono. Sessel probably is just done. Unless IL changes, I'm not sure there needs to be any work on it. Certainly the people on the mono team I expect they're passionate enough that if there is any work needed, they would do it, because they would use it for some things. So I'm not sure. Yeah, I don't know what its official status is, but I also wouldn't expect it to break necessarily. It's kind of a, in most of the, well, when we change the runtime or the language, or we do hot reload or whatever, it's not often that new IL.
monoSysL doesn't support very well things like the analyzer generated code that actually give you something you can't do with exceptions.
Oh.
Because you can't access the source code where it's coming from.
Oh, I see. Yeah. Well, that might be a separate thing because in the case of generated code, it doesn't exist. So, you know, that, yeah. Yeah, I don't know specifically, that one's an interesting case. But yeah, I would expect that mono Cecil is like, I would expect that if it needed to get updates, it would probably get updates because it has a passionate community of people who use it. And mono is still a going concern until, you know, the grand unification of everything. But even then, there's probably going to be something that can be used instead of Cecil for those scenarios. But I don't know. This is not an official statement.
Cool. Well, would you thank David for joining us this evening and for his talk tonight?
Thank you very much.
Cool.